Hello everyone, welcome to the channel. So in this series of sorting techniques, we will now move forward towards learning heap sort. So heap sort in the series of sorting techniques is based upon a heap data structure, and in order to understand heap sort properly, we'll first let's dig into the heaps and how they are implemented. So before heaps, heap sort is a type of comparison based sorting algorithm that basically sorts an array in an ascending or descending order, and by transforming it in a binary heap type of data structure. Okay, and it basically uses you know the concepts of max heap and min heap, where in max heap the largest element is the root, the node one, and in the min heap the smallest is the opposite, the root node. Min heap is the opposite of max, or you can say max is the opposite of min. So the algorithm uses the binary heap data structure to efficiently sort the elements. At the start of the video, like I've told you, heap sort is based on the heap data structure. So this algorithm uses the binary heap structure to efficiently sort the elements. And the idea for heap sort is like based on selection sort, like where we find out the max element and swap it with the last element. So we'll do just like that, but in a different manner. Okay, so now let's talk about heap. So heap is a complete binary tree. Let me just draw the tree. Okay, so first we will talking about heap. So heap is a complete binary tree, and it is a kind of tree whose all nodes are completely filled except the last one, or you can say the leaf node. So this is the leaf node. Okay, last node is not filled, but I can see the complete tree is filled. Okay, and if I take another example, this can also be a complete binary tree because all my nodes are completely filled, so I can also say complete binary tree. Okay, so it's a complete binary tree we can see, and it will fill from left to right from last nodes. Okay, uh, now if I say one more example. Okay, so in this case, it's not a complete binary tree. Why it's not a complete binary tree? As we can see, it's not filled from left to right. Okay, this node is not filled from left to right, and leaves are always filled from left to right. Then it will be a complete binary tree. But in this case, it's not a complete binary tree. Okay. Yep. So the final thing would be complete binary tree is a kind of tree where every level except the last level is completely filled. All levels are filled, and in case of last level or leaves, it will be filled from left to right. So in heap, we usually follow the concept of min or max heap, and using min or max heap, we will sort our program. Okay, so first we have to construct a min or max heap uh, through the given set of array provided to us. Okay, so let me create a min and max heap. Okay, so min heap would be like let's suppose 5, 6, 7, 8, or okay, 10. Let me do 10, 11, 12, and 13. Okay, and in case of max heap, 18, 15, 10. Okay, so in min heap, like earlier I told you, in min heap we see the parent node, it will always be smaller than its child node. Okay, so like here we can see 5 is the parent node and it cannot have child nodes greater than uh, its own, element. So 5 is smaller than 6 and 7. So uh, we have in min heap the smaller node as the parent node. Okay, and it will be smaller than the child node. The max heap would be the opposite, where we see root would be greater than its child elements. Now we have checked and seen what min heap and max heap is. Now we will learn about the operation heapify. So heapify is a process where we convert an array into a max or min heap, and it's a process of creating a heap data structure from a binary tree, where we will create a min or max heap. Okay, so usually we will perform like max heap and then we do the heapify operation. Okay, so let's take an array and we will do the heap sort or perform the heap sort on this array. So I have an array as 10, 20, 30, 40 and 50. So I will be creating a complete binary tree from this. It will be 10, 20, 30, 40 and 50. This will be my 0, first and second height of tree. Okay, so these are the height of tree. So height of tree is 2 here, and it will be my 0th index. It will be my first element, third, and it will be my fourth element. Okay, so we can see where here we have created a min heap. Now why I have selected this only array, because we have to learn about two operations that we are going to use in our heap sort. So those two operation are up heapify and down heapify, where we do the addition and subtraction. So let's suppose I have an element, parent index. I have selected this element as 1, and if I wanted to access the left and right child, then we do the operation as li and right I. So the formula for this is 2pi plus 1. So in my case my parent index is 1, so 2 multiplied by parent index plus 1 will be 3. In this case 2 multiplied by parent index plus 2, so in this case 2 multiplied by 1 plus 2 is 4. Now my first index here is 20, and second and third and fourth are 40 and 50. So we can get the right and left child nodes of the parent element. Similarly, if I wanted to add data in the fifth index here, if I wanted to add 60 in fifth, so for that we have a formula, as I have to find the parent of this newly added element as I wanted to add. So I need to check like where I have to add. So I need to pass the child index minus 1 divided by 2. So this will be the fifth element. So I'm going to add in the fifth index only. Now I need to calculate its parent. So the formula is child index minus 1 divided by 2 is 4 by 2 divided by 4 by 2 is 2. So I will be adding it in the second index. So not in the second index, parent index will be 2, and I will be adding this as a child of parent second index. Okay, so parent will be second index, that is 30, and we can add its child at fifth index. Now to use heap sort, let me take a different array, because the above one is a sorted one. So I have taken array 14, 20, 13, 15 and 4. Okay. Now, so there are certain steps of heap sort algorithm that we just have studied, and to reiterate each and everything, the first step is we need to build a max heap from the input data. So input data is present. Input data is 14, 20, 13, 15, and 4. Okay, and with this we have to build a max heap. The first step is to build a binary max heap from the input data, and this will be done by transforming an array into a complete binary tree where the largest value is at the root node. Okay, now we in the next step we will swap the first and last elements of the array. After building the max heap, the largest value will be at the root because we have built the max heap, and we will swap this value with the last element of the array. This will place the largest value at the end because at last I have the smallest one, and I will swap with this, which is at the final position in the sorted array. Okay, now we heapify the remaining data after swapping the first and last elements. Then the heap size is reduced by 1. Then root node may now violate the max heap property, as I will swap it with the last element. So the algorithm needs to reheapify that data to restore it to the max heap. So again I will swap the data that I put at the start of the element. You will find this familiar when I show you with the example. I'm just reiterating the step. Now we will repeat the above two steps until the heap size is reduced to 1, and at the end we will be returned with the sorted array. Okay, so now let's start. So first we have to create a complete binary tree by converting the array to a tree. So the tree would be in this form: 14, 20, 13 would be here, 15 here, and 4 would be here. Okay, now in this step 2 we need to convert this to a max heap. So in max heap we have parent as the largest and the child as the smallest one. This would be the step 1. This would be step 2, convert to max heap. Step 1 I have done, where my job was to convert the array or the data to complete binary tree, not the BST. Next step would be to convert it to a max heap. So here we can see 20. Okay, now 14 is smaller than 20, then we do the swap. Okay, so it would be now 20, 14, 13, 15, and 4. Now I can see 15 is greater than 14, then I'll also do the swap. Now 20, 15, 13, 14, and 4. Okay, so next element was 14 after 20. Now we do the swap, and after that it was 15, so we do the swap. Now we got the max heap. So once a tree is converted to a max heap, we do the heap sort. So like I've told you, for heap sort we need to find the maximum element here. So our parent obviously is the maximum element in case of max heap. So we do remove this and we perform the heapify operation. So here we remove the 20. Okay, and we swap it with the smallest one at the end. Now 4 is at the start, 15 here, 13 here, and 14 is here. But again I see it's not max heapify, so we need to do the reheapify operation, and we need to repeat our step 2 and 3. So 4 would be swapped with 15. 15 is here, 4 comes here, 13 comes here, and my 14 would be at end. But I can see it's still not the max heap. Now we remove, earlier we removed the 20, and we have 4 as the root, so we have to do the reheapify. Again at the bottom we need to see the smallest one. Now we have left out with this element. Now again I'm going to do the reheapify, and it would be like this: 15 would be at the top, 14 would be here, 13 would be here, and 4 would be here. Okay, so after performing the reheapify, we have left with this. Now we will now do heapify again on this. Now we will remove the maximum element or the root element 15 and swap it with the smallest one at the end of the node. So 4 is at the end of the node, so we will swap with this. So we will again left with 4, 14 and 13. Now I can see again we have to perform reheapify here. Okay, so now we again swap this with 14, 4 and 13. Okay, now 14 will be removed from here because the largest element, and it will left with 4 and 13. Okay, now again if I do the reheapify, so it will be like 13 and 4, and at end I will be removing my 4, so I will left out with the fourth element only. So at the end, at last I will be left out with the 4, only a single element. And now I can see my arrays also been sorted. Okay, so we return the sorted array after the heap size has been reduced to 1. Now the array is sorted and we can return this as the final result. So in this step for 1, we build a complete binary tree, then we convert it into a max heap, then we heapify this complete binary tree. Okay, then we have the max heap. When in that we remove the max greater element at the top of the node, then we do the heapify. Okay, then we repeat the step and remove the max element, then again we do the heapify operation. So in this way we do the process, and at the end when we left out with the only a single element, we find the array is sorted. Okay, so now we have to also do the time complexity of heap sort. So for time complexity in heap sort, as you can see, the height of a complete binary tree is always equal to log n. So complete binary tree, as we usually form here, so its time complexity is log n. So this is because for a given node in a binary tree, there can be at most 2 child. Okay, it cannot have more than that nodes. Okay, so this further drives us to a point where at each level or height of a binary tree, the number of nodes will almost equal to half the number of nodes present in the next level. To put in a simple way, in a binary tree, the number of nodes at each level is almost double the number of nodes at the previous level. Okay, so we can see at this level I have 1, then at the previous level it will be double the 1. Okay, so it means for a binary tree with the height h, the total number of node will be in a mathematical computation, if I do n is equal to 2 raised to the power h, 2 1 2 2. Okay, then it will be up to 2 and h minus 1. Okay, from mathematical induction we also know that this will be equal to 2 raised to the power h minus 1, and therefore it would be like log of 2 n plus 1. Therefore the height of binary tree is almost equal to this. This indicates basically that if a number of nodes double, the tree will increase by one level, only one level. From this we can conclude that the complexity of this heapify function that we have done at the end would be nearly equal to big O of log n. Okay, and therefore the worst case time complexity of heap sort is big O of n log n. Why? Because the worst case occurs when we wanted to sort a list in ascending order, but actually it was arranged in the descending one. So we have to do the operations again and again. And in average case also, when the list is arranged in a jumbled way, then also we have to do in the same time complexity big O of n log n. So for worst, we will also do big O n log n, and in the average one also, best case would be big O of n. Okay, because the best case occurs when the list is already arranged in the desired order, and in this case there is no need to heapify the tree. It removes the factor of log n. Overall, the so complexity results uh, in big O of n. The space complexity will be of heap sort is big of n. This is because we have used a fixed number of variables, and we haven't used the extra memory space like we have used in the previous counting and the quick sort, but we haven't utilized the extra memory space apart from the loop variables and the auxiliary variables that included in this. Okay, the largest one, and so it means the that we can sort an array containing 1,000 elements even without using the extra variable. Now the main question or the question usually asked in the interviews, when to use heap sort. So heap sort is often used when the data size is quite large, and we have a limited amount of memory available, and in that only we have to do computation. So since heap sort is an in-place sorting algorithm, it would be more utilized and memory efficient than other sorting algorithms like quick and merge sort. So heap sort is also used when stability is important, such as when sorting a list of records based on multiple fields. And heap sort can also be used in alternative to quick sort where the data is already partially sorted or data has a lot of repeated values. Okay, so in these cases, heap sort we can use, and time complexity wise also heap sort is I see much better than the quick sort. And in the space complexity wise, we can see that heap sort has a much better space complexity than the one with the quick sort of big O of n plus n. Okay, so this can be utilized. Okay, so this is the dry run of heap sort. Now let's move towards the program for heap sort. Okay, so now we will be doing the program for heap sort. Let's write public static void main. Inside this, we will be defining an array R. Okay, so let's define an array. And I will be creating two methods. My first method would be to sort the array, and second would be heapify. Okay, so first I will be creating the sort one. Here I will be taking the array, and next would be heapify. In this method, I will be taking the array n, and also I element also. Now first, as I have already defined the n, so let's also define here also. Next I will be iterating a loop. Okay, with this for loop we will be creating a complete binary tree for int I equal to n divided by 2 minus 1 and I greater than equal to 0, I minus minus. So from here I equal to n by 2 minus 1 is basically we have computed the height of tree, and then we will heapify this. So we will pass our array n and I. Okay, now after this max heap is constructed for this complete binary tree, then we will do the sorting. So for that we will iterate our loop from the top of the array. Okay, or I would say the maximum element, because in the max heap the max we will be considering. So int I equal to n minus 1, I greater than 0, I minus minus, and we will do the swapping. Okay, so int temp, and here I will be picking the array of I, not the I 0th one, because I have to swap it with the smallest one, and then I have to remove the small and do the heapify again. Okay, so array of I have to put in the temp at the end, so that is why I have also iterated it from the end, because in the max heap what we will construct, we have the largest or the greater element at the top of the node, at the parent node. So we will pick the parent node. That is why we iterated this loop from the end, and we will put this element at the end of the array. Okay, so array of, not here, array of I, we will put array of 0. Okay, and for array of I will be putting this. Okay, so 0th will be my largest. I have added in temp, and then I have left out with the, okay, I think mistakenly added this. Yes, then array of I largest I will be putting at 0. Yeah, this is correct, and array of I is temp. Yeah, so at the 6th I have added the smallest one. I is the last one, and then again we will do the heapify. So here I will be passing my array, and n would be I, and it would be 0, because largest would be the 0 one. Now in the heapify we will do the operation that I have shown you. So first I will be picking the largest node. My node would be I. Now I'll be picking the left node. It would be 2 multiplied by largest node, or not the 2 multiplied by I, because it would be same largest. I can also pick plus 1, and I will be pick my right node, 2 multiplied by I plus 2. Okay, now I will be doing comparison. If my left node is less than n, and array of left node is greater than array of largest node, then my largest node would be left node. Okay, and in case my array of right node is less than n, and array of right node is greater than array of largest node, then my largest would be right node. But in any case, when these two are passed, so I also need to swap, and if my largest is not equal to I, in that case only I will be doing the swap. So array of largest node I will be then placing in the temp variable. Okay, or I can say the I also, because we have, so I can also I or largest, you can anything you can pick. Okay, not the same, because I we have let's suppose it was the second index, and now we have added the left index. The child one is the greater one than the I, so I have to put I in the temp, and in array of I, because we have to do the swapping, then in the parent I have to put the largest node, and in again array of largest node, temp would be added. Okay, and then again we will do the heapify to see if other elements are smaller. Then I will be passing array n and the largest node. So what we have done here, we have swapped with the array of I that we got, and largest is the one then we have added in the array of I, and temp we have added in the smaller one. Okay, so let me run this program. Okay, I need to also call this. So heap sort object dot sort we will call, and inside this we will be passing our array, and now we will calling for loop. Okay, I just missed a semicolon. We have done everything correct, I think. This method is correct, heapify is good, comparisons are good, and then we picked up from here. Sorting is good, looping is good. Okay, I think okay, I got the because I have printed I, not array of I here. Okay, now it will give us the correct sorted array. Okay, we can see the sorted array, and we can see it's sorted out. Now for this I'll just debug this, and let's do this. Okay, I'll just put some breakpoints here and also here. Now let's do the debug, and here also. So you see this has been arranged to a complete binary tree. Okay, now we will do the max heap operation. So for max heap we get the element n equal to 6, length is 6, I we picked as 2, so 13 is here. Okay, now my largest node is 13, left node is 5 and 6, so I've computed left node values 2 multiplied by I. My I was 2, so 2 plus 2 multiplied by 2, 4 plus 1, 5, and this will be 6. Okay, 5 and 6 we can see. Okay, now we see left node and right node. So my 5 is less than n, it will be good. Array of left node, array of fifth index we can see, but array of sixth index we cannot see. So this condition will fail here. We can also see this. Now my array of left node is 0, 1, 2, 3, 4 and 5, 7. 7 is greater than the largest node. No, it's not greater than, so it will reject this, and we will again do this operation of max heap. Now 1 is my largest node. Okay, and left node is 3 and 4, so left node here is 11, and I is 1, and my next node, left node here is 3 and right is 4, so 3 here is 3 is this one 5, so 5 is okay, 5 is greater than the 1. No, this will fail also, and right node will also fail. Now we will move here again, we will heapify. Now it will give us I as 0. Now we see I as 0. Okay, and it will be as 1 and 2. Okay, now we have 12, 11 and 13, but I can see 11, it will not, again left node is it, these are in this way, so it's not greater than, but the right one is greater than, so we do the swapping here. Now let's again go to this debug one. Left is fail. Now right node is my 2. 2 is less than n, n is 6. Array of 2, second index is 13, that is greater than the 0th index, so it will do the swap. Largest node now changes its value to the right node. Largest node is 2, it's not equal to I. Now we will do the swapping here. Now you will see the swapping is done. Now it will again see, okay, 13, 11 and 12. Now it will see left and right are smaller, or any one is greater than, it's not. Then again we will go. Now we will perform the heapify operation, and we can see our max heap is built here. It's like 13, 11, 12, 5, 6 and 7. Now we will pick 13 and swap it with the smallest element in the array with 7. Okay, now we go down. Now I can see I swapped with 13. Okay, so here now again I do the heapify operation. Now my next element is 13 has been placed here. Now my heap is left out with this one, 12, 11, 7, 5 and 6. Okay, because I have removed this one. Now 12 is the greatest. It will swapped with the sixth element. Okay, now let's see. You can see swapping has been done. So in this way we will move towards each and every element and we will do the swapping. So in this way we will sort this complete array and we will get our elements in this heap sort. So I think that's it for today, guys. Thank you. And if you have any doubt and queries regarding heap sort or any other algorithm, do comment and I will be happy to help.